Okay, round two. Hope that everything about yesterday was okay in terms of the equilibrium equations of acids. Again, it's just taking what you know and applying it to new situations. And that little trick about putting the Ka over the reactants above the product and getting your and getting your KEQ for that equation. So just a sec. Yep, it's definitely reactants over products. So let's have a look at measuring acidity. So today is going to be about how can we measure how acidic something is. So I want you to sort of take your mind and realize that acidity really is a measure of how acidic something is, obviously, but in Bronsted-Lowry, remember that it's about equilibrium, and so really it's about how many ions are pushed into solution, and so you can favor the reactants or products, and we're going to look today at how pH fits into equilibrium. So we'll start off with a little poem. For coffee, it's 5. For tomatoes, it's 4. While household ammonia is 11 or more. It's 7 for water if in a pure state, but rainwater is 6 and seawater is 8. It's basic at 10, quite acidic at 2, and well above 7 when litmus turns blue. Some find it a puzzlement. How about you? And so, of course, today we're talking about pH, which is used to express how basic or acidic a substance is. Now, notice that pH can also tell you how basic a substance is. It's not just about how acidic something is, it can also be basic. So that's what pH is used for, is how acidic or basic something is. But we are also going to use it to, in many different situations, and we'll learn all about that. Okay, so again, remember that you can tell from this poem that it's quite acidic at 2. So the lower the number, the more acidic it is. And so it's basic at 10. The higher the number, the more basic it is. Just as a reminder, the pH scale goes from 1 to 14. Oh, sorry, it doesn't. It goes from 0 to 14, actually. So the most acidic thing something could be is 0, and the most basic something could be is 14. Okay, and we're about to learn why, actually. Because it has everything to do with the concentration of ions the concentration of ions in solution. And the maximums make those numbers, not humans. Let's take a look at how to calculate pH. You have to use logarithms. So for those of you in math, you probably have already finished this unit if you've taken Math 12 this semester. And for those of you who haven't, you're just going to have to get used to the log key on your calculator. And so pH is a measure, is calculated directly off of the concentration of acid. And so this is the little formula for how to calculate it. To find the pH, you have to take the, notice, negative log of the concentration of acid in solution. So this, remember, is a formula. You can use this formula for 2 reasons. Number one is you could calculate what the pH is. You could also reverse engineer and calculate what the concentration of the acid is, in which case you'd have to take the anti-log, which is simply 10 to the power of a number, but 10 to the power of x would be an anti-log. But in any case, this is how to find out the pH. If you know the acid concentration, you put it there, you take a log of it and make it negative. So just flip the sign. So we call it an inverse log. Very similarly, the pOH is found. Now, you've probably never heard of pOH before, but it's the same idea. It just tells you how basic something is. So again, the lower number, the more basic it is. So the pH and pOH scales are just dead opposite. So if it was a pH of 2, it would be a pOH of 12 because the scale goes from 0 to 14, and they're just opposites. But in any case, to calculate the pOH, it's the same formula, but notice that instead of the acid concentration, we're dealing with the hydroxide ion concentration there. Okay. And so what I want you to do now is review the process of how to take a log and anti-log on your calculator. So we're going to pause the video and we're just going to stop here and make sure that everybody in the room knows how to use the log function on their calculator or the anti-log. You need to do both. Usually that anti-log function is inverse or second function of the log, but not always. So go ahead and make sure that you learn how your calculator works, and we can pause it right now. Oh, and to test it, sorry, don't pause it right now. To test it, just make sure you can get your calculator to take the anti-log of 4 and see what the answer is. Okay, and when you have the answer, if you can get that correct, then you know how to use it. Okay, so go ahead and pause it. Okay, so hopefully the anti-log of 4 you got was 10,000. Because again, anti-logs are just 10 to the power of, and so that would be the anti-log of 4. Right. So hopefully you know how to use log and anti-logs on your calculator. The other thing you're going to be using today is the pH loop handout. It looks something like, let me open it up for you just a sec. It looks something like this. Okay, and what happened there? Yeah, that's right. Looks something like this, and again, this pH loop what this is for is it's for telling you how to convert between all these things. And notice what I've already put on the screen is here to go from pH to H3O. But over here also it tells you how to go to OH and POH, and then there's in the middle how to switch back and forth. So this pH loop is just summarizing what I've already sort of said today. But I haven't talked yet about the KW down here at the bottom, how to get between the ion concentrations. Okay, so take a look at that pH loop scale. I'm just going to close that and get back to where we were. Okay, and so what we're going to do is find the POH and pH of a 0.5 molar solution of HNO3. Now notice that it does not give us the concentration of OH whatsoever, so to find the POH, according to these equations up here, we're going to need to know the concentration of OH. But remember that there's lots of ways, there's lots of ways to find the POH other than using the OH concentration. Like look at your pH loop, you could also just know the POH by figuring out the pH, and that's what we're going to do in this example. So look there at what we have. We know that HNO3 is a strong acid from the strong acid charts. Therefore, we know that the ion concentration of acid is going to be equal to whatever the concentration was of HNO3, because it doesn't maintain equilibrium. It's a strong acid, so if it was 0.0125 molar acid, then HNO3, we know that that's the concentration of hydronium ions in the solution. If it wasn't like that, we'd have to do some EQ, some KEQ work to figure out the actual concentration of the acid in this case. But that was easy enough because it's a strong acid. It's pretty straightforward. And again, we're going to use the equation from the top there. pH is negative log of that. You type that into your calculator and you get this. Okay. Now, in pH and POH, you really want to focus on the decimals after, or sorry, the digits after the decimal, and those are significant. And so there we go. We have the POH is the pH is 1.9, and you see that the negatives have canceled out. That's why we don't say that it's a pH of negative 1.9. It's a pH of 1.9. Okay, so it's really easy to find the POH from this. So take a look at POH, and all we have to do is take 14, which is the maximum pH, away from the pH, and that is 12.097. So approximately 12 would be the POH of it. Now POH, if it's a high number of POH, that means it is extremely acidic. So you have to watch out which scale you're using, if it's pH or POH, because a high number on the pH scale is basic and the high number on the POH scale is acidic. So careful there. Okay, so let's do another example. Let's try to find both concentrations of both the OH ion and the hydronium ion if we know the pH is 4.322. Okay, so again, to do this, look at your pH loop, and you will probably notice that we're starting at the pH, right? And you want to know the concentration of H3O. And so how do you get there? You're going to take the antilog of the negative pH. So we're doing the math just in reverse. So first we're going to take the pH and make it negative from what it currently is, and then take the antilog of it. So that's just inverse log. So you can see that we're going to take the antilog of negative 4.322, because that's what the pH is once it's negatived, and then you put it to the 10 to the power of negative 4.322, and you get this number. Okay, so that there is, you notice it's in molar, is the concentration of H3O. Okay, so we would put H3O here. Okay, and so there you have it. And of course you round to sig figs. But then to find out the concentration of OH, you're just going to do what we learned, the formula that we learned in the previous days in Ka, Kw, and Kb, and that is also in the pH loop down at the bottom. So the concentration of OH again is calculated by taking Kw and dividing it by the acid. Remember that Kw is the limiting factor. It's what keeps everything in equilibrium. So you just put Kw over top of the concentration of the acid, like so, and you will calculate the concentration of OH ions in solution, because the Kw is always the KEQ equation for water. So water has to maintain that concentration. So then you have the 2.10 times 10 to the negative 10 molar OH ions in solution. So they're both there, just in a different concentration. Yep, and we have done that example as well. So that pH loop is very important to know and have memorized. So make sure that you, you already know some of it. Some of it's quite easy and natural, but knowing what to do when will keep that map nicely done in your nice in your brain, and you'll be able to use it whenever you want. Just a note at the end that because the hydronium is in greater concentration than the hydroxide, the solution is acidic. Okay, so don't use pH unless you're talking about 25 degrees Celsius, because remember that pH is based off of 25 degrees. So the equilibrium numbers are based off pH. So yeah, the solution is acidic because we know that the hydronium ion is greater than the hydroxide ion. Okay, so for today, go ahead and do 49 to 47, and that is all. Thank you.